Radiation is dangerous. Everybody knows this. You keep radioactive material far away from your house, far away from your children, far away from your food and your bed and your breakfast table. You lock it up behind thick concrete, behind walls of lead, in laboratories guarded by serious people in white coats with little clicking machines. That is what civilized, sensible human beings do. And if somebody were to suggest that we deliberately put a piece of radioactive metal inside an ordinary home, up in the ceiling where a family sleeps underneath it every single night, well, you would say that person is a maniac, a lunatic, somebody you would want to call the police about. And yet, right now, as you are listening to me, there is almost certainly a little piece of radioactive material somewhere in your house. It is probably above your head. It was installed on purpose. In many places, the law actually requires it. Millions upon millions of these little radioactive gadgets have been manufactured, sold, and screwed into the ceilings of bedrooms and kitchens and hallways all over the world. And almost nobody, not one person in 100, loses a minute of sleep over it. So either we have all lost our minds, or there is something about this story that the simple version gets completely, spectacularly wrong. I am going to argue to you over the next little while that the simple version is not just wrong. It is wrong in a way that matters. It is wrong in a way that, once you see around it, teaches you something important about the difference between what frightens us and what actually hurts us. The people who designed this little radioactive gadget and put it in your ceiling were not maniacs. They were, in fact, absolutely clever. And the reason we all agreed to let them do it turns out to be one of the most elegant little stories in all of applied physics. Let me start by being fair to the fear. Because the fear is not stupid. The fear of radiation comes from somewhere real, and I would never want to talk anybody out of it by pretending there is no reason for it. There is a reason for it. Several reasons, in fact. Think about Marie Curie, a brilliant woman, 2 Nobel Prizes, one in physics, one in chemistry, which is something almost nobody has ever done. She worked with radium for decades, carried little vials of it around in her pockets, marveled at the way it glowed in the dark on her desk at night. Her notebooks, her papers, her furniture, her cookbook from the kitchen, all of it is still too radioactive to handle safely without protection. She died of a blood disease, and most people now believe the radiation was the cause. Think about the young women who worked painting watch dials in New Jersey in the 1920s. They used paint made with radium because the radium would glow, so you could read the time in the dark. The bosses told them to lick the tip of the brush between strokes to keep a fine point. They swallowed tiny amounts of radium thousands of times every day for years. And then, slowly, terribly, their jaws began to rot. Their bones crumbled. Many of them died in their 20s and 30s in a way that is painful even to describe. Think about what happened at Hiroshima and Nagasaki. Think about the workers at early reactor sites who got sick. Think about all the careful rules about shielding and distance and time that every nuclear technician learns before they are allowed near anything hot. There are good reasons, real reasons, sensible reasons for being extremely careful around radioactive material. The fear is not irrational. The fear has a history written in suffering. So, given all that, given this enormous, expensive, sometimes tragic reservoir of human experience, which teaches us that radioactive material should be handled with enormous care, what on earth are we doing putting it into the ceiling of almost every bedroom in the country? Either we are all insane, or there is something about the word radiation that is hiding more than it reveals. I want to suggest to you that it is the second one. The word radiation is one of those words that sounds like it describes a single thing, but when you look underneath, it actually describes a whole family of very different things. And treating them all the same is like treating all liquids the same. You drink water. You do not drink gasoline. You especially do not drink mercury. They are all liquids. But if you walked around terrified of every liquid because some liquids can kill you, people would think you had lost your grip on reality. And yet, when it comes to radiation, that is almost exactly what we do. Let me tell you what is actually in your smoke detector. If you took one of these things off the ceiling and opened it up, which I do not necessarily recommend, but if you did, you would find a little metal cup, about the size of a shirt button, and inside that cup there would be a tiny amount of a silvery metal called americium, specifically americium-241. The total amount is unbelievably small. We are talking about something like 1/4 of a microgram. A microgram is 1/millionth of a gram, and a gram is about the mass of a paperclip. So you are looking at roughly 1/4 of a millionth of a paperclip's worth of this stuff. It is less material than a single grain of salt, much less, and it is pressed into a thin foil between layers of metal so that you could not get it out even if you wanted to. Now, that tiny speck of americium is radioactive. It is steadily, patiently shooting out little invisible bullets, billions of them every second, all day, every day, year after year. This has been going on inside your ceiling for decades, if you are unlucky enough to be in an old house with an old detector. And this is not a bug. This is the whole point. The detector cannot work unless that metal is throwing off those little invisible bullets. At this point, a sensible person should be standing up and shouting at me, "You just told me radium killed people. You just told me radiation is dangerous. You just told me Marie Curie's cookbook is too hot to handle. And now you are telling me there is a piece of this stuff shooting out billions of bullets per second above my bed, and you think this is fine?" Yes. I think this is fine. I think this is in fact one of the cleverest things anybody has ever done. And to show you why, I have to tell you something about the little invisible bullets. Because not all invisible bullets are the same. And this is where the word radiation starts to come apart in our hands. When something radioactive decays, the atom is unstable, and it has too much energy, and it needs to get rid of that energy somehow. It has several ways to do it. The 3 classical ways are called alpha, beta, and gamma. Alpha, beta, and gamma. You may have heard the words. I want you to forget whatever you thought they meant, because the differences between them are not just technical differences. They are enormous, practical, life or death differences. An alpha particle is a fat little lump. It is 2 protons and 2 neutrons stuck together. That, by the way, is the same thing as the nucleus of a helium atom, which is a lovely coincidence worth thinking about for a moment. Alpha particles are heavy, as subatomic things go. They are slow, as subatomic things go. They carry a positive electric charge of +2. And they are clumsy. Oh, they are clumsy. An alpha particle is like a drunk rhinoceros blundering through a crowded room. It cannot move an inch without bumping into something. A beta particle, on the other hand, is a tiny little dart. It is just an electron flung out at tremendous speed. It weighs almost nothing compared to an alpha particle. It carries a single negative charge, and because it is so small and so fast, it can slip and slide through matter much more easily than the rhinoceros. A gamma ray is not a particle in the same sense at all. A gamma ray is a piece of light, very energetic light, light so energetic your eyes cannot see it, but light all the same. It has no electric charge at all, no mass, and it travels at the speed of light, naturally, because it is light. And because it has no charge, it has almost nothing to interact with. Gamma rays slip through matter like a ghost through walls. Now, here is the question that matters. If these 3 kinds of radiation are flying toward you, which one should you be most afraid of? Your instinct, if you are like most people, says the biggest, heaviest one. The rhinoceros, the alpha. That sounds like the one that would do the most damage. A bigger bullet hurts more than a smaller bullet, yes? Well, hold on, let's think about this more carefully. It is true that if an alpha particle hits a living cell, it does tremendous damage. More than a beta, more than a gamma. It is a heavy, charged, clumsy bruiser of a particle, and it rips molecules apart as it passes through. On a per-hit basis, the alpha is the nastiest of the 3. But there is a second question, and it is just as important as the first. How likely is any given alpha particle to reach a living cell in the first place? And the answer is barely at all. Because the alpha particle is so clumsy, so heavy, so electrically loud, it bumps into everything. A single alpha particle flying through the air will slam into air molecules so often that it dumps all of its energy in about an inch or two of travel. An inch or two. That is it. An alpha particle could be blasting out of a lump of americium at thousands of miles per second, and it will be dead and still, just a harmless helium atom, before it has traveled the width of your hand. A piece of ordinary paper stops alpha particles cold. The outer dead layer of your own skin, the part that is already flaked off and going to fall off next week, stops alpha particles cold. You could hold a piece of pure alpha-emitting material right against your palm, and the radiation would never get through to a single living cell. You see the trick now. On a per-hit basis, alpha is terrible. But alpha cannot reach you. It cannot get in from outside. The only way alpha particles can hurt you is if you somehow get the source inside your body, if you eat it, or breathe it, or get it into an open wound. Once it is inside, now all that per-hit nastiness is happening right next to your living cells, with no skin to shield them. That is why the radium girls died. They were swallowing radium, which decays by alpha, and the radium settled into their bones where the alpha particles could shred the bone marrow from the inside out. Not from outside, from inside. But from outside, in the open air, separated from your skin by even a sheet of tissue paper or the dead outer layer of your body, alpha is the most harmless of the three. The fear of the biggest bullet turns out to be upside down. The biggest bullet cannot reach you. Beta particles travel much further, several feet in air. They can make it through paper. They can even get a little way into your skin. You need a thin sheet of plastic or aluminum to stop them reliably. Gamma rays, the ghost radiation, travel for enormous distances and pass right through you. To stop gamma rays, you need serious shielding. Lead, concrete, dirt. This is why the atomic bomb is so devastating, because it produces huge bursts of gamma rays and fast neutrons that pass through walls and bodies like nothing is there. This is why the workers at reactors wear monitors and stand behind lead glass. Gamma is the one that really gets you from a distance. So the picture we started with, the simple radiation equals danger picture, is already falling apart. Alpha, beta, and gamma are about as different from each other as, I don't know, a thrown baseball, a rifle bullet, and a radio wave. They all move through space, sure. But calling them all radiation and being equally afraid of all of them is like being equally afraid of baseballs, rifle bullets, and radio waves, because they can all move through space. It is a category error. And it is a category error that smart people made for a long time, including some of the early scientists, because the differences were not obvious from the outside. Now let me tell you why this matters for your smoke detector. The stuff inside your smoke detector, the americium-241, is an almost pure alpha emitter. Yes, there is a tiny bit of gamma along with it, but the dominant thing it spits out is alpha particles. And we just said what alpha particles do in air. They go an inch or two, and they stop. Which means the alpha particles coming out of the americium in your smoke detector have almost no chance at all of reaching you, even if the detector is right above your head. They are eaten by the air in the ceiling. They are eaten by the little plastic housing of the detector itself. They are eaten by the dust on the bookshelf. Every little molecule of air between the source and your body is a tiny invisible shield, and there are billions upon billions of those molecules in the way. The dose of radiation you get from a smoke detector on your ceiling, measured carefully, is so small that it is essentially lost in the background. The natural background radiation you receive every day of your life, from the rocks under your feet, from the bricks in your walls, from the potassium in your own bones, from cosmic rays hitting you from outer space, all of that adds up to far, far more than anything your smoke detector is doing to you. You get more radiation from eating a banana than from sleeping under a smoke detector for a year. A banana has potassium in it, and a tiny fraction of natural potassium is radioactive potassium-40. So if you are worried about the americium in your ceiling, you should stop eating bananas first. Actually, no. Do not stop eating bananas. That is a joke. The bananas are fine. The ceiling is fine. Everything is fine. But okay, say you believe me that the alpha particles cannot get to you. Fine. What good are they then? Why did we put the radioactive metal in the detector in the first place if the radiation it throws off cannot even reach out of the device? This is where the design becomes beautiful. Because the whole point is not for the radiation to reach you. The whole point is for the radiation to do a very specific job inside a very small enclosed space, just a few millimeters across, and then die. Let me explain how a smoke detector actually detects smoke, because until you know this, the use of americium will not make sense. Inside the detector there is a little chamber, about the size of a thimble. This chamber has two metal plates in it, one on top, one on bottom, held a small distance apart. There is a battery, a regular 9-volt battery, connected to those plates. The battery puts a small electric voltage across them. One plate is positive, the other is negative. Now, ordinary air is mostly empty space with some molecules bouncing around in it. Nitrogen, oxygen, a little carbon dioxide, water vapor. These molecules are electrically neutral. They have the same number of positive protons inside their nuclei as they have negative electrons buzzing around them. So if you put two charged plates with air between them, you might think nothing happens. And for the most part, you would be right. Normal air does not carry much electric current. It is actually a pretty good insulator. But here is the trick. Put the little piece of americium right there between the plates. The americium is throwing off alpha particles. Those alpha particles go smashing through the air between the plates at high speed. And when an alpha particle crashes into an air molecule, it knocks an electron off. It ionizes the molecule. The molecule, which was electrically neutral, now has a positive charge because it has lost a negative electron. And the electron that got knocked loose floats around as its own little negative entity. So where before you had neutral air molecules, now you have positive ions and free electrons. And those are charged. And the electric field between the plates grabs hold of them. The positive ions drift toward the negative plate. The negative electrons drift toward the positive plate. And that drift of charged particles is a tiny electric current flowing between the plates. So the americium is creating a steady, faint little electric current through the air by continuously ionizing the air molecules. This current is tiny, microscopic, but it is steady, and the electronics in the detector can measure it. The detector sits there year after year, measuring this steady trickle of ionization current. As long as the current is flowing at its normal value, everything is quiet. Now, what happens when smoke comes in? Smoke is not gas. Smoke is a cloud of very tiny solid particles. Little specks of soot, little droplets of unburned stuff, little bits of whatever it is that is on fire. And these smoke particles, although they are tiny from our point of view, are enormous compared to individual air molecules. A single speck of smoke might have the mass of thousands or millions of air molecules. They are like boulders floating among sand grains. When smoke drifts into the little chamber, the ions and the free electrons that were drifting across the gap bump into the smoke particles and stick to them. And now, instead of having many tiny, fast-moving charge carriers crossing the gap, you have a few big, slow smoke particles with charges stuck to them lumbering across. The current drops. The trickle becomes a drip. And the electronics notice. And the alarm goes off. That is the whole thing. That is the entire physics of an ionization smoke detector, which is one of the two main types in use. There is a continuous drizzle of alpha particles ionizing the air. The ionized air carries a little current. Smoke interferes with the current. The interference triggers the alarm. That is it. Now you see why we need the radiation. The alpha particles are the thing making the ionization. Without the alpha particles, you have no current to disrupt. No current to disrupt, no way to detect smoke. You could try to ionize the air with, I don't know, a high voltage, but that would eat batteries. You could try to do it with heat, but that would be unreliable and would also eat power. The americium does the ionization for free. It is a tiny self-powered ionizer that never stops, never needs to be wound up, never needs to be plugged in. It just sits there doing its job. And now you see why alpha is exactly the kind of radiation you want here. We need something that will ionize air molecules aggressively. Alpha does that wonderfully because it is so electrically loud and clumsy that it cannot go near an air molecule without knocking an electron off. And we need something that will not leak out of the device and reach people. Alpha does that too beautifully because it dies within an inch or two of its source no matter what you do. The alpha particle is almost custom made for the job. It is the perfect tool. You could not use gamma. Gamma would ionize air, sure, but gamma would also pass through the whole device and keep going, across the room, out the window, and down the street. That would be genuinely bad for you, and it would also waste almost all the energy doing nothing useful. Beta would be better than gamma, but still too leaky. Alpha is the only one of the three that will stay inside the little chamber and do its work and then just stop. It is like choosing the right tool. You would not use a sledgehammer to put in a thumbtack. You use the alpha, because the alpha is the thumbtack-sized tool for the ionization-sized job. And we are not finished with the cleverness. Because the choice of the specific element, americium-241, matters just as much as the choice of the specific type of radiation. You need an alpha emitter. Fine, there are lots of those. Radium is an alpha emitter. Plutonium is an alpha emitter. Polonium is an alpha emitter. Uranium is an alpha emitter. So why americium specifically? Let me count the reasons. First, the half-life. The half-life is the time it takes for half of the atoms in your sample to decay. If the half-life is too short, the detector will stop working in a few years because all the americium will be gone. If the half-life is too long, each individual atom decays too rarely, and you do not get enough alpha particles to make the ionization current you need. You need a Goldilocks half-life. Not too fast, not too slow. Americium-241 has a half-life of about 432 years. That is perfect. In a human lifetime, or even over several human lifetimes, the amount of americium barely changes. You could install one of these detectors when your grandfather was born and it would still be hot enough to trigger today. And at the same time, 432 years is short enough that with just a quarter of a microgram of the stuff, you get plenty of decays per second to do the job. Second, the energy of the alpha particles. Americium puts out alpha particles of about 5.5 million electron volts. I know that is a funny unit, but just think of it as a certain amount of kinetic energy per particle. That energy turns out to be in just the right range to ionize lots of air molecules before the particle stops. Higher energy would travel a little further, but not help us. Lower energy would travel less and might be absorbed too quickly. Americium is right in the sweet spot. Third, the purity. Americium happens to be a very clean alpha emitter. It does not produce much beta. It produces very little gamma, and the little bit of gamma it does produce is low energy, easily absorbed by the metal casing of the detector. You could pick some other alpha-emitting isotope and end up with unwanted beta and gamma tagging along, which would complicate the shielding and the safety calculations. Americium does its job with almost no mess. Fourth, the chemistry. Americium is a solid metal at room temperature. It does not evaporate. It does not react violently with the air. It can be pressed into a thin foil and sealed between layers of metal without any fuss. If it were a gas, or a volatile liquid, or something that corroded easily, it would be a nightmare to work with. Instead, it is a quiet, stable, mechanically well-behaved material. Fifth, and this one is quite wonderful, the price. Americium is not rare once you are in the business of running nuclear reactors. It is actually a byproduct. When you run a reactor to produce plutonium, you inevitably produce some americium along the way, because some of the plutonium captures extra neutrons and decays down into americium. So once the reactors were running for other reasons, mostly military reasons, there was a steady little trickle of americium coming out the side, essentially as waste. People were looking for something useful to do with it. Which brings me to the history. Element 95, americium, named after the Americas, in the same way that europium was named after Europe. It was first produced deliberately in a laboratory at the University of Chicago during the Second World War as part of the Manhattan Project by a team led by Glenn Seaborg. The year was 1944. The world was on fire and the laboratories were running day and night, and a group of scientists were bombarding plutonium with neutrons, trying to see what new elements they could make that did not exist anywhere in nature on Earth. It is one of those funny stories in physics. The element americium was not named in a press conference. Seaborg supposedly announced its existence on a children's radio quiz show because the patents and the military secrecy had not yet caught up. A boy on the show asked him if any new elements had been discovered recently, and Seaborg said yes, two, actually, americium and curium. And that was how the world found out. For the first 20 years or so after its discovery, americium had no obvious everyday use. It was an interesting curiosity, a heavy synthetic element that you could study if you happened to have access to the expensive reactors that produced it. But it was piling up. The weapons programs were generating more and more of it as a byproduct. And somewhere along the way, somebody had the idea that an alpha emitter with a long half-life might be useful for detecting smoke. The earliest smoke detectors, in the 60s, were expensive industrial devices, mostly used in factories and commercial buildings. The home versions, cheap enough for ordinary families, started appearing around the end of that decade and really took off in the 1970s. That is when the design with a tiny button of americium-241 sealed inside a plastic housing connected to a 9-volt battery and a cheap little beeper became standard. It is an absolutely extraordinary consumer product when you stop and look at it. It runs for years on a battery the size of a matchbox. It has essentially no moving parts. It requires no maintenance beyond changing the battery. And it saves lives, a lot of lives. Studies done over the following decades showed that houses with working smoke detectors had roughly half the fire death rate of houses without them. Half. You cannot buy a piece of safety equipment for $10 or $15 that has a bigger life-saving effect than this little radioactive button in the ceiling. So here is where the argument really flips over, because we have to start comparing dangers. We cannot just say radiation, bad. We have to ask, compared to what? The danger of dying in a house fire, if you do not have a smoke detector, is real. It is not hypothetical. People die in house fires every year, many of them in their sleep, because smoke can kill you before the heat or the flames even reach you. Carbon monoxide in particular will just put you to sleep and you never wake up. A smoke detector gives you, on average, precious extra minutes to wake up, get out, save your children. That is the real benefit. The danger from the americium in the detector, meanwhile, is so small that it has never been reliably measured against background. People have tried. You can run the numbers. You can make reasonable assumptions. You get a risk number that is hundreds or thousands of times smaller than the ambient natural radiation you are exposed to just by being alive on this planet. It is swamped. It is invisible. It is a number so small it is essentially a mathematical curiosity rather than a real threat to your health. So, on one side of the scale, real, measured, frequent deaths in house fires. On the other side of the scale, a theoretical, unmeasurable, essentially imaginary tiny increase in radiation exposure. Which side do you want to take? This is not a hard choice once you look at it clearly. The smoke detector is not even a little bit of a trade-off. It is overwhelmingly, screamingly, obviously worth it. You would have to be confused in a very particular way about what radiation is and does to refuse to put one in your ceiling. And now I want to tell you that there is a second kind of smoke detector, the photoelectric type, which does not use americium. The photoelectric detector uses a little light-emitting diode and a light sensor and detects smoke by the way smoke particles scatter the light beam. It is a perfectly good detector, and in many ways better than the ionization type for certain kinds of slow, smoldering fires. Many modern detectors combine both technologies into one unit. You can absolutely have a working smoke detector with no radioactive material in it whatsoever, and lots of people do. So why am I making a fuss about the ionization type? Because the ionization type is still extremely common, because it was the original design, and because the question of whether it is safe to have in your house is the question that exposes how confused we are about what radiation actually is. The photoelectric detector gets around the issue by not using radiation at all. But the ionization detector walks right up to the issue, puts a piece of radioactive metal in your ceiling on purpose, and says, "Look, this is fine. Here is why." And when you understand why, you have learned something that applies far beyond smoke detectors. You have learned that radiation is not one thing. You have learned that alpha, beta, and gamma are as different as they can be. You have learned that the same word covers phenomena that behave completely differently in the real world. You have learned that a particle which is devastating inside your body can be completely harmless a few inches away in the open air. You have learned that fear of a name is not the same as fear of a thing. You have learned that physics does not care how scary something sounds. Physics only cares what actually happens. Measured, counted, worked out. I want to push on this point a little more, because I think it is the real lesson hiding inside the smoke detector. We human beings have a habit of being afraid of words. Somebody says radiation and our stomachs tighten. Somebody says chemical and we get suspicious. Somebody says nuclear and we imagine mushroom clouds. The words carry emotional weight that is often wildly out of proportion to what is actually being described. Water is a chemical. Oxygen is a chemical. Your morning coffee is a chemical. The potassium in a banana is radioactive. The carbon in your bones is partly radioactive. The word nuclear just means relating to the nucleus, which every atom has. If we let the words do our thinking for us, we would not be able to drink, eat, or breathe. Because everything is a chemical, almost everything emits some radiation, and every atom is nuclear. The trick, and this is a trick that takes practice, is to keep asking about any scary word. Compared to what? How much? What kind? Can it reach me? How does it actually work? These are the questions that physics forces us to ask. And when you ask them, the terror usually drains out of the word, and what is left is just the specific thing, with its specific size, its specific properties, its specific place in the world. The designers of the smoke detector asked those questions. They asked them carefully. They asked them quantitatively. They asked, what is the dose? They asked, what is the type? They asked, what is the worst case? They asked, what is the benefit? And the answer came back. Negligible dose, most forgiving type, worst case no worse than a banana, benefit saves thousands of lives per year. So they put the radioactive metal in the ceiling, and they were right to do it. And we were right to let them. I would like to take this lesson one more step, because I think it matters. What else are we wrong about? In the same way we were wrong about this. What other perfectly useful, wonderful, life-saving, or simply interesting things do we turn away from because the word attached to them scares us before our minds can catch up and do the actual thinking? I am not going to give you a list. Making the list is your homework, not mine. But I will tell you that the list is longer than you would expect. And I will tell you that the people who can shake off the fear attached to the word and look coolly at the thing itself tend to end up doing useful work that the people stuck on the word cannot do. The americium in your ceiling is, when you understand it, a little monument to that idea. Every time that little gadget beeps when the toast burns, It is, in a sense, also beeping to remind you that once upon a time, some very patient, very careful people looked at a word that frightens ordinary people, broke it apart, found what was useful inside it, designed something clever, and put it to work. The radioactive metal is not there in spite of the laws of physics. It is there because of the laws of physics. Because those laws, studied carefully, told us that this particular isotope, in this particular amount, sealed in this particular way, would sit quietly and helpfully doing its little ionization job for hundreds of years, long after the house around it has fallen down, long after we are all gone. And for its whole life, it would hurt nobody and it would save somebody. That is not a maniac's idea. That is a beautiful idea. That is the kind of idea that makes me want to stand up and cheer. And the next time you hear a smoke detector chirp, or you change the battery at the kitchen table, or you curse at one of them in the middle of the night because something in the oven is smoking and the whole house is howling at you, I would like you to pause just for a second and think about the little speck of metal up there, older than almost anything in your house, quietly firing off its billions of alpha particles per second, each of them traveling about an inch and then stopping forever, each of them leaving behind a little wake of ionized air that is even now trickling across a pair of metal plates, so that if any real smoke comes along, the trickle will change and the beeper will scream and you will have your chance to get out. That little button of americium was made from plutonium in a reactor during a war. It was a byproduct of the worst weapons humans have ever built. And somebody took that byproduct and thought about it and found a way to use the quietest, safest, most local form of radiation it throws off to wake people up when their house catches fire. I think that is one of the most hopeful stories I know. Out of the Manhattan Project, we got a lot of terrible things. We also got this: a tiny helper in every bedroom, powered by a speck of artificial metal that barely exists anywhere else in the universe, whispering its alpha particles into the dark, watching for smoke while the family sleeps. So the next time somebody tells you that radiation is always and everywhere to be feared, you can tell them about the piece of radioactive metal on the ceiling of their own bedroom, and how it has been there for years, and how it has probably never given them a bad day, and how it might, one night, save their life. And if they do not believe you, tell them to ask the alpha particle how far it can travel through air. Ask it, and listen carefully, because the alpha particle will answer the same way it always does. Not very far at all, thank you. Just an inch or so, just enough to do my job and no further. And then ask yourself what else in your life you have been afraid of without ever checking how far it could actually reach. Tell me what you think about this little invisible helper in your ceiling. Has knowing what is up there changed the way you feel about it, or not? I want to hear your honest answer.